right, this question reads, which symbol represents a component whose resistance is designed to change with temperature? Let's go through them one at a time and really explore the physics in each one. So this is the symbol for a variable resistor. Okay, so this is not the right answer. It's not designed to change with temperature. It's designed to change with sort of the operator's control so that we can sort of slide. So this is like a dimmer switch. If you have a knob that you turn and it makes the light dimmer, then you're making there's more resistance. The charge is going through more resistance, and so the light becomes dimmer. Or you can turn the knob the other way, or sometimes it is an actual sliding sort of switch, and you slide it back, and then there's less resistance, and so the light gets brighter. So this is a variable resistor. It acts just like a metallic resistor. You can just sort of adjust how much of the metallic resistor that the charge is flowing through, right? And so we've talked previously about an equation for resistance based on sort of what metal it's made of, its resistivity, the length, and that's really the key here. As we increase the length that the charge is flowing through, there's going to be more resistance, right? Because the area of this is staying the same. So this is the equation for resistance in terms of its resistivity, the length of the metal, and the area of its cross section, usually a circle for cylindrical wires. And so that's just another chance to review this idea. Greater length, greater resistance, more resistance, dimmer light, right? Less current. All right. Let's be careful about saying that, less current. So there'd be more voltage sort of dropping across this at more resistance. If it's a series circuit, right, then the current's going to be the same everywhere in that series circuit. All right, this is a thermistor, the symbol for a thermistor, a thermal resistor. And so it is the correct answer to this question. It's the symbol that represents a component whose resistance is designed to change with temperature. You can have negative temperature coefficient thermistors, positive temperature coefficient thermistors. They have sort of different curves. And as the temperature changes, they're either going to increase or decrease in temperature depending on whether it's sort of positive or negative. But this is a non-ohmic component because the resistance sort of depends on temperature, right? And sort of think about Ohm's law as being when the potential difference and the current through are in proportion. You know, they're sort of always in the same ratio, so they give us a constant resistance. This is an LED. So the symbol here is for an LED, and its IV characteristic, if we plot sort of current against voltage, its IV characteristic looks like this. So there is a threshold voltage where it starts to conduct. If we were to take the inverse slope of this part of it, then we could calculate sort of, well, what is the resistance of this LED after its sort of threshold voltage? But because this doesn't create a straight line IV characteristic, it's a non-ohmic component. In other words, there's places where it does not obey Ohm's law. If we have a flat line like this on an IV characteristic, remember that the resistance is V over I. So if we plot voltage against current like this, then it's just sort of the slope of this gives us the resistance. So when we did our resistance lab, we just said, well, we'll plot the voltage on the y-axis against the current on the x-axis, and that way the slope is our resistance. But then we get introduced to this idea of IV characteristics, where we like to plot the current on the y-axis. And here we've got to remember that if we want to know what the resistance of this is, then we're going to take the slope, but take 1 over the slope. In other words, the slope of this is equal to 1 over R, right? We got to take the inverse of the slope because the resistance, remember, is V over I. So the slope of this is I over V. And so if we just calculate the slope of this, the rise over the run, then we got to remember that that's not equal to the resistance. It's equal to 1 over the resistance, right? So we have to sort of take the inverse of both to get back to the familiar Ohm's law. So keep that in mind. If we keep the same idea in mind right over here, we'd say, okay, well, what's the slope of this? 0. What's the inverse of that? And now we have to sort of say, well, we'll take the inverse of 0, 1 over 0. But we can say that it's infinite, okay? That here, you can basically think about until we cross over the threshold voltage, which is usually about 0.6 of a volt for most LEDs, until we exceed the threshold voltage, this thing has infinite resistance or nearly infinite resistance. Okay? And then it will start to conduct, and it sort of behaves more like an ohmic component, where it obeys Ohm's law as this sort of climbs up. Then we could take sort of the slope of this, 1 over, R would be equal to I over V, or the slope, the inverse of the slope would give us sort of the resistance here. But that's what the IV characteristic looks like for an LED. Now this is called a light-dependent resistor. Okay, this is a light-emitting diode. This is a variable resistor, VR, variable resistor. So a light-dependent resistor is kind of like the thermistor in that it's designed to change with, instead of temperature, it's designed to change with light, right? So these are supposed to be light rays. And as light is incident upon the resistor, the light-dependent resistor is usually made of a semiconductor material. And so it doesn't have free or conduction electrons. You may recall that when we derived the equation for mean drift velocity, I equals NAVE, we have to sort of use the idea of free or conduction electrons. The number density tells us the number of free or conduction electrons per unit volume. Well, semiconductors don't have any free or conduction electrons. They need to have energy input into them to sort of liberate the energy to free them up so that they can more readily conduct. And one of the ways to provide that energy is with light energy. And so the resistance of these LDRs actually goes down as you put light on them. And so when light shines on an LDR, it frees up more conduction electrons. And so the charges can more readily conduct, through this because you're getting sort of more conduction electrons. And so the resistance actually goes down. There are questions that will require you as a student of pre-ACE and ACE physics to remember that what happens to the resistance of this kind of a component when there is light or in the dark. There'll be some clue in the question about, it's light or at nighttime, it could be a night, sensing light, so it knows to sort of turn on. So when there is light shining upon it, that's when the resistance is going to go down. And again, I can't sort of just, study that by trying to commit it to memory. When there is light, resistance goes down. You could try to just remember it that way. I want to think through all the physics of what's happening. So I think these are made of semiconductors that kind of hold on to their electrons a little bit more tightly than the good conductors like copper. So we need some energy input, and that's what these sort of arrows remind us. There's some light energy that's going to free up the electrons, that's going to sort of get them away from the nuclei so they can conduct more readily. And when we have electrons conducting more readily, there's less resistance to the flow of charge, right? So we're decreasing the resistance of an LDR in the light. In the light, the resistance goes down. So that's such a noteworthy statement. You might want to actually write it down in your notebook. The resistance of an LDR decreases in light. When light is incident upon the light-dependent resistor, the resistance goes down or decreases. But the correct answer to this question is B. That's the symbol for the thermistor. Use each question as an opportunity to explore all the physics, because even though this question was about a thermistor, you could imagine or anticipate questions about the IV characteristic of an LED, or a question like what's going on with the resistance of an LDR. So in a problem study, use each question, kind of explore all the physics contained there, and even the incorrect answers got some good physics in it. We'll see you next time.